In this video, we introduce the concept of an acid-base titration, and we'll run a numerical problem to illustrate it. Okay, so acid-base titrations are an example of something more general called volumetric analysis. Okay? And the idea is as follows. You're going to have a solution that you want to characterize. Okay, so this is just a flask with some solution that you're interested in, and there are some properties that you don't know anything about. For example, you might know what the volume is, okay, but you don't know what the molar concentration of that species that you have is, and you would like to determine it. Or perhaps you want to identify what the molar mass of the substance that you have in that unknown solution is. Okay? Now, that is going to be called the analyte. That is what you're trying to analyze. Right, so a way to analyze this substance is to actually make it react with something else until the stoichiometric or equivalence point. Okay, so the idea is that to this solution, you now can add a reactant that is going to react with it. Okay, and you know everything about that reactant. Okay, you put this reactant in something that is called a burette. Okay, and both the concentration of this solution and the volume that you have to add in order to fully react it with the analyte, those two things are known. Okay, so using stoichiometric calculations, then you can finally come to your molar concentration or molar mass. Okay, so again, that is the analyte. That is what we want to analyze. And again, we're going to add here something that is called the titrant, and again, that is well known. Right, the key is to be able to detect quite well what is the point that is called the equivalence point or the stoichiometric point at which you have the stoichiometric amounts of the two reagents added so that the reaction is complete. Okay, and this is generally done by use of an indicator. Okay, and we will actually talk much more about indicators in the second semester in acid-base reactions. But in essence, you actually add here something that is going to change color whenever you reach the stoichiometric point. Okay, so whenever you have added enough volume, okay, so you start here, and then maybe you have to add this much volume. Whenever you have added exactly the amount that you need to reach the stoichiometric point, then there will be a change in color in the analyte solution, and that will tell you exactly what is the stoichiometric point. Okay, so the idea here is that to apply this to an acid-base reaction where we're going to have an acid and then a base. Okay, to generate water and then a salt, in this case AB, which we're going to make be aqueous. Okay, and again, the idea is that here maybe this is the acid. Okay, and then you might know the volume, but you don't know the concentration, and that is the base. Okay, so when this neutralization takes place, in this particular point, when you add exactly the same amount of moles of base as you have on acid, in this case the stoichiometry is 1 of acid to 1 to base. When you get to that point of the same number of base added as you have of acid, then you reach the stoichiometric point, you reach the neutral point, and there should be a change in color here in the analyte solution. Okay, so to illustrate numerically how this works, we're actually going to run a problem in which we want to calculate here what is the molar concentration of a solution of acetic acid, okay, CH3COOH, aqueous. Okay, we have 25 mL of this weak acid solution, and then we're going to titrate it with sodium hydroxide. Okay, aqueous. Okay, and we know what the concentration of that sodium hydroxide is. It turns out that we actually have a concentration of 0.302 molar sodium hydroxide that we're going to put it here. Okay, and again, this is going to generate water, H2O liquid, and then a salt, which in this case is going to be sodium acetate, CH3COO, which is soluble. All right, so again, we load the burette to the top, and then we start to add base, sodium hydroxide, and no color changes. The sodium hydroxide continues to be added until you reach a point where the color change. You measure that volume, and that volume for this particular example that we have here happens to be 34.3 mL. Okay, so when you add 34.3 mL of the sodium hydroxide base that is 0.302 molar concentration, then you reach the equivalence point. The question is, how can you use this to determine what the molar concentration of the acetic acid that is your analyte, how that works, okay? How that's going to be. All right, so notice what we're going to do here. The idea is that with the molar concentration and the volume, you can get the moles of base that you have added exactly, okay? Now, because these two things are related stoichiometrically, if you know the moles of base that you have added for the reaction to be complete, then you know how many moles of acid have reacted as well, again, through stoichiometry. And if you know the moles of acid that you have reacted and you know the volume, then you can know the molar concentration. Okay, just a little bit about the equations. The molar concentration is equal to the number of moles divided by the volume of the solution. Okay, so notice that in this case, what we're going to do is we're going to calculate first the moles of base. We know that, right, because we have the molar concentration and the volume, so we can get the moles of base. Then from here, with the stoichiometric calculation, we will get the moles of acid. And if we have the moles of acid, because we have the volume, then we can calculate what the molar concentration is. Okay, so we can get finally to the molar concentration of the acid. So I'm going to do all of these calculations at one time. Okay, let's see. Moles of base. Again, we're trying to solve for that. So it's going to be molar concentration, which in this case is 0.302 mole of sodium hydroxide per liter. Okay, multiplied times the volume. So we have added 0.0343 liters of the sodium hydroxide concentration. Notice that I have to change the units of volume from milliliters to liters so that the calculation actually works out, okay, so that the units cancel out. Okay, so up to this point I have the moles of base. Now I carry out the stoichiometric calculation and notice that I have 1 mole of acid, 1 mole of acetic acid, CH3COOH, for every mole of sodium hydroxide. Okay, so this calculation allows me to transform from moles of sodium hydroxide to moles of acetic acid. And finally, I can just find what the molar concentration is by dividing the number of moles of acid over the volume of my acetic acid solution. And again, here we also have to use liters so that the units of the molar concentration happen to be molarity. Okay, so you type this in your calculator and you find that the solution to this is 0.414 molar concentration. Okay, so this has been a video in which we have explained the concept of an acid-base titration, and we have solved a numerical problem to illustrate it.